Well, chemical reactions. Chemical reaction is a chemical change. We have one or more substances that we're starting with that change into other substances. What's happening in a chemical reaction is just a rearrangement of the atoms, connecting them in different ways to form new molecules. The atoms themselves are unchanged. So it's like building with Legos. You take two Lego things and you take them apart and you make something new. The Lego bricks are exactly the same, but they look different because you put them together in a different way. That's what's happening in a chemical reaction. We describe chemical reactions using an equation, much like we describe things in math. The general form is that we put the reactants on the left side, and then there's an arrow instead of an equals that's going to the products. So the reactants react to produce the products. There's a lot of information in a chemical equation. We have the formulas of the reactants and products. Oftentimes we'll have the states, gas, liquid, solid. We have the relative numbers of molecules for each reactant and product. And from that information, we can figure out masses of reactants used and products made. The symbols that we use to indicate the state are pretty straightforward, but let's just go over them. These are in parentheses after a chemical formula. G stands for gas, L for liquid, S for solid, AQ stands for aqueous. Aqueous means that it's dissolved in water, a water solution. So let's look at the combustion of methane. Methane is a large part of natural gas, and when it burns, it combines with oxygen to form carbon dioxide and water. It also gives off a lot of heat, and so the water that's formed here is in the gas state. Anytime something is burning, it's combining with oxygen. And that's something you should remember, because if I ask you to write a combustion reaction, I'm not going to tell you that one of the reactants is oxygen. You need to remember that. Burning, combustion, always involves oxygen. So if we look at this chemical equation here, we have the formula for methane. I don't expect you to know what that is, but there it is. Reacting with oxygen. We write O2 here because oxygen is one of the 7 diatomic elements. And then we have this arrow, and this shows that we're producing carbon dioxide and water. But there's something wrong with this equation, because chemical equations are supposed to tell us the numbers of particles that react. And so here, if we look at the oxygens, we have 2 oxygen atoms on the left side of this reaction, and 2 oxygens here and another one over there, so 3 oxygen atoms. So this seems to imply that an oxygen atom is being created out of nothing. Is that possible? No. Just like Lego bricks just don't materialize in midair. If we look at the hydrogens, there's also an issue with the hydrogens. Over here we've got 4 hydrogens, and on the right now we only have 2 hydrogens. So 2 hydrogens have gone missing. So this equation we say is unbalanced. We need to balance it because we know that in actual fact the number of atoms of each kind of element stay the same in a chemical reaction. They're just rearranging. So it's not that nature is wrong, it's that our equation is wrong. The equation violates the law of conservation of mass. So we can fix that. So we balance the equation. When we do this, we can change the number of different molecules, but we can't change the formulas. Okay? So here we have methane, and here we have oxygen. So we can say now, well, let's say there's 2 oxygen molecules. But we can't change this to O3 just because that would make it balanced, because O3 is the formula for something else. So you can't change formulas. So if we have 2 of these oxygen molecules, that will give us a total of 4 oxygen atoms. And over here in the carbon dioxide, there were 2 oxygen atoms, and 1 water molecule gave us 1 oxygen, so now we're also going to have to put 2 water molecules over here. And this is also going to take care of the problem with the hydrogen. Now there are 4 hydrogens over here and 4 hydrogens over there. So if you think of these as kind of funny Lego bricks, you can imagine taking this one apart and taking those 2 apart and putting them back together like this, right? And you'd have just the right number of pieces to do that. That's what always happens in a chemical equation. Mass is conserved, cannot be created or destroyed. Any questions yet? Balancing equations is something that some students struggle with a little bit, and I think it's because you don't see the big idea behind it. If you can see this picture in your mind, then balancing the equations isn't bad at all. So we have steps. The first thing you need is the formulas for the reactants and products, and sometimes we call that a skeletal equation, just the bare bones, right? Then you're going to balance the atoms, and this is a method called balancing by inspection. And so 3 people could balance the same equation, and they might go about it in different ways. There's not one right way to do it. We're just all going to come up with the right answer at the end. So as kind of a guideline, balance atoms that occur in more complex substances first. Leave any free elements for last. So if you, like the O2 there, it was just oxygen, it wasn't mixed up with any other elements, that's a good one to leave for last. It's possible to end up with coefficients that are fractions. It's also possible to completely avoid doing that, but if you get fractions, you need to get rid of them by multiplying everything by the denominator of the fraction. And then you should always check your equation. So let's do a couple of examples. And we'll get a little bit of a review of nomenclature here too. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So we've got words there. We're going to take this word sentence and make it into a chemical equation. So when it says and, that's going to be like the plus sign. And to form or to produce, that's where the arrow goes. Solid carbon dioxide and carbon monoxide gas. So we need the formulas for our 2 reactants, silicon dioxide and carbon. What kind of an element is silicon? Metal, non-metal, or semi-metal? It's technically a semi-metal, but it's on the non-metal side. So, your book never talks about what do you do with the semi-metals. My observation is that if the semi-metal is on the non-metal side, for nomenclature, treat it like a non-metal. If it's on the metal side, treat it like a metal. So silicon being on the non-metal side, silicon dioxide, this is a molecular compound. Silicon and oxygen, 2 non-metals. So what's the formula going to be? SiO2. The di tells me that there's 2 oxygens, and there's no prefix for the silicon, so that's just one of them. I am given the states, the physical states. It says it's a solid. So I'll put an S there. And then a plus. And just to make things easy on myself, I'm going to leave a little gap here in case I need to write something in front of the next element, next compound. Solid carbon, it says. So C is the symbol for carbon. Now that's an element. We have to ask ourselves, is it one of the 7 diatomic elements? No, it isn't. So then we just leave it alone. If it was a diatomic, then we need to write a 2 after it. This is also a solid, so we put an S. And then we've got the arrow. And we've got solid silicon carbide. Well, that one might be a little tricky. It says silicon carbide, and we're treating them both as nonmetals, but there aren't any prefixes. What's the one prefix that we sometimes just leave out? 1, right? So this is SiC. I would not expect you to get that, but I used to be able to ask Siri what the formula for silicon carbide was, and she'd tell me it was SiC. She didn't do that anymore, unfortunately. So that's also a solid. So S here. And carbon monoxide gas, what's the formula for that? CO. Carbon with 1 oxygen, and that's a gas. Any questions so far? So there's our skeletal equation. Now we need to balance each individual element. A lot of times you could just start with the first element. What we're going to do is we're going to count up how many silicon atoms are on the left side of the arrow and how many are on the right side of the arrow. Because we can sort of think of this as being like a balance beam or a teeter-totter. And we want it to be the same on both sides. So over on the left side, I have 1 silicon atom, and on the right side, I've got 1 silicon atom. So those are fine. I can leave them alone. Over here, there are 2 oxygens. And how many oxygens total on the right side? Only 1. How can I make there be 2? I could have 2 carbon monoxides, right? So I'll just put a 2 in front of CO. I can't change the formula, but I can say, well, there must be 2 of them. So now I've got 2 oxygens. And on the left side, I have 1 carbon. There's no carbons over here. And on the right side, I have a carbon here and 2 carbons there. Total of 3 carbons. 3 carbons on the right. I need 3 carbons on the left. So I think I'm done. And now I should go back and check. So I got 1 silicon and 1, 2 oxygens, 2 oxygens, 3 carbons, 1, 2, 3 carbons. So there's my balanced chemical equation. Any questions? Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So again, we're given words. So combustion of ethane in which it combines with, so combines with is like the plus sign. Combines with, to form is our arrow, and we've got gaseous carbon dioxide and gaseous water. So the first compound, we're given the formula because we haven't taught you how to do that one. So C2H6. It says it's a gas, so I'm going to write G after it. Bunch of words in the middle there which don't matter. Combines with gaseous oxygen. So plus oxygen. Is oxygen a diatomic element? Yes, it is. So I need to write O2. Writing chemical equations is where this is going to be really important that you know the diatomic elements. Because if I write O in here, it's going to be incorrect. It's O2. And that's a gas. And then I put an arrow. And I'm looking at my products. This time I have carbon dioxide. So that's CO2. And that's also gas. Plus gaseous water. So water in the gas state. So we can balance this by inspection and just go back and forth, and that works for a lot of things. I also want to show you another method that some of you might like. If you don't like it, don't worry about it. You don't have to use it. So In this method, we're going to just sort of use the space underneath to keep a tally of what's going on here. And I'm going to start by just putting a big line down the middle, because that's going to divide the right from the left and tell me where my sides are. Then I'm going to make a list of the different elements, and I just go in order as you encounter them. There's a carbon, there's hydrogen, and there's oxygen. Those are the three elements in this equation. Now I'm just going to mark how many carbon atoms are in this compound. So there's 2. And then I look at that compound, well, how many hydrogens? Well, there's 6 hydrogens. How many oxygens? None. Zeros and O's get confusing, so I'm just going to put a line there because there's none. Over here in the oxygen, I've got no carbons, no hydrogens, I've got 2 oxygens. And then over here, this is 1 carbon, no hydrogens, 2 oxygens, no carbons, 2 hydrogens, 1 oxygen. This is more useful for complicated things where maybe you tried doing it just the first method, just going back and forth, and you realize, okay, this is getting ugly. Then start over and maybe keep track this way. So now I've got my list of everything that's in here, my inventory. So I'm going to look at carbon. On the left side, I have a total of 2 carbons, and on the right side, I have a total of 1. I need them to be the same. I can't get rid of any of these, but I can make more of those. And I do that by putting a 2 in front of it. If I have 2 CO2s, then that affects all the numbers underneath, right? Now I've got 2 carbons and 4 oxygens. So my carbon line is good. I've got 2 and 2. For hydrogen, I've got 6 on the left and 2 on the right. What do I need to multiply 2 by to get 6? 3. So I put a 3 in front of this, and there's no carbons, so that's not going to change. This is going to become a 6, and this is going to become a 3. You following? So now I've got 6 and 6, that's good. Now I get to my oxygens, and I've got 2 here, and I've got 4 plus 3 is 7. What do I multiply 2 by to get 7? 3.5, right? 7 halves would do it. Most students don't really care for fractions, so let's avoid using the fractions. This is what I call the odd-even problem. Here I've got oxygen atoms coming in pairs, and they're always going to come in pairs. And over here I need an odd number. I changed my pointer by accident. I've got an odd number that I need. How do you make an odd number into an even number? Multiply by 2. So what I'm going to do is I'm going to multiply everything by 2. So I'm going to put a 2, actually let's change this, go to a different color. I'm going to put a 2 here, so that's going to change this and this. That's what I'm messing with, so I'm going to leave that one open. I'm going to change this to a 4. That becomes a 4, this becomes an 8. I'm going to change that 3 to a 6. So now I've got 12 and 6. I just doubled everything except that oxygen. And what's 2 times 2? It's 4. I don't know what I was thinking. When I doubled both sides, my carbons and my hydrogens are still balanced. I didn't mess them up. There's just more of them, right? Now with my oxygens, this is the one I have open. I like leaving this one for the end because when I change this, I don't mess up anything else. If I change this one, I'm changing carbon and hydrogen. If I change this one, I'm changing carbon and oxygen. When I add a coefficient in front of the O2, I'm only changing the oxygen. It's not going to mess up anything else. For the oxygen over here now, I have 8 plus 6 is 14. Well, that's easier to get, right? I need a 7 in here. It's not a very nice 7. 7. And there's 2 oxygens in every one of those, and so that gives me 14. Combustion reactions are where you're most likely to end up with this odd-even problem. You can do it with a fraction, but you can also just double everything to get rid of the odd numbers. Any questions? Let's do another one. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. So here we have ionic compounds. We're going to need to figure out what the ions are. So lead-2 nitrate, what does that Roman numeral mean? It's a 2+ charge. It's not how many there are. That's lead with a 2+ charge. What's the formula for nitrate? NO3 with a -1 charge. So if I put those two ions together, what will my formula be?
PB parentheses NO3.
Yeah, PB with NO3 in parentheses and a 2 on the outside. Because I need 2 of these to make up -2 charge to balance the +2 charge. And then I'm told that that's aqueous, so I'm going to write AQ. Plus potassium chloride. Well, what's the charge on potassium ion? +1. It's in group 1. And chloride? -1. So the charges are opposite but equal, and so we just need KCl. Again, aqueous. To form lead-2 chloride. This is that same lead ion, but now it's going to be with chloride. So I need 2 chlorides for the Pb2+. PbCl2. This ion only has a single atom in it, and so I don't need parentheses. I'd understand what you mean if you put the parentheses, but it looks silly. And S for solid. And then potassium nitrate, that's this potassium and the nitrate ion. And we just need 1 of each. So we push them together, KNO3, and that's aqueous. Any questions about how I got this far? So writing formulas for compounds like this is something that's on the exam on Wednesday. Now I need to balance this. This equation has polyatomic ions. Well, one polyatomic ion is this nitrate. And we have nitrate as a reactant, and there's nitrate as a product. The nitrate ion stayed together. It was shrink wrapped. It doesn't come apart, it just got combined with something else. So we can treat that as a single unit instead of balancing the nitrogens and the oxygens separately. You can do them separately if that makes more sense to you. So I'm just going to start at the beginning, because I find that works most of the time. Start with the first element and just work your way across. If you start going in circles, you find that you're changing things over and over and over again, just stop and start over somewhere else. It's also important to make sure that your formulas are correct, because if the formulas are wrong, it may be impossible to balance. So I have 1 lead ion here, and how many on this side? Just the 1, right? So that's fine. How many nitrate ions? 2. And how many on the right side? Just 1. So if I put a 2 in front of the formula, now I'll have 2 nitrate ions. Did that change the lead on the right side? This didn't affect that at all. So I didn't mess up my lead. So now I've got these 2 taken care of. Now I'm going to look for K. Potassium, I've got 1 over here, and I've got 2 over here. So if I put a 2 in front of KCl, now I've got 2 potassiums. So I've got 2 Ks here and 2 Ks there, and that didn't mess with lead or nitrate. And then the chlorine, I've got 2 chlorines here, and how many chlorines over there? 2. Balancing ionic equations usually comes out nice at the end. Any questions? This is something you need to practice.